This is Computing Up, conversations about computation writ large, with Michael Littman and Dave Ackley. This episode was recorded May 16th, 2022.
Hey, Dave, how's it going?
I'm doing all right, stressing about way overdue writing. How about you?
I guess today is the day that I officially have been, or an announcement has been made that I am actually going to be the division director for information intelligence systems at NSF. So the AI funding, HCI funding, information sciences, databases, all that, I don't know, whatever, quarter of $1 billion is going to go through me.
Okay, well, we're totally scared of you now. And well, congratulations. Now it can be told.
Now it can be told because there was a public, I guess, just a presentation from the computer science director at SAIS, and it's like, hey, just by the way, we're also getting some new division directors, and so there's a picture of me going so it's like, okay, there's the guy. Yeah, I would definitely trust him with that amount of money. That seems totally
so
fine.
When do you have to show up in DC?
I am in our townhouse in Alexandria, Virginia, as we speak.
Wow.
So we just took possession of the townhouse today, and I set up the internet like within 15 minutes of getting here, and I was like, oh, it's like every other place now.
You haven't found the roaches yet.
Well, hopefully, when we that's right, in Atlanta we had some issues with bugs, but I think it'll be fine. The only kind of bugs I expect in DC are listening devices.
That's right. Russian roaches. And well, so that's an exciting adventure underway.
Yeah, so hopefully I will keep you informed as to what interesting things are happening there until such time as the government says you need to stop talking about us on your podcast, at which point I will stop talking about us on the podcast.
But you'll tell us that that's why you're stopping talking about it.
I will, because I'm not great at certain kinds of secrets, because that's something that everybody should know. Freedom of Information Act, something, democracy.
Yeah. If they don't like it, they'll like it. You'll make them like it. That's your superpower.
So between the last two times we talked, I think I was back in Rhode Island, and haven't done much in terms of stuff with the department there, but there was a cool talk given by one of my colleagues, Ellie Upfall, about some of his award-winning research. And when I was there, I got to see a ton of the faculty in the department, and it was a fun afternoon because I want to say almost everybody who I wanted to see, but that's then anybody who I didn't see is going to be mad, but whatever. The point is they don't listen to the podcast. So
they'll never know.
Pretty much anybody who is willing to talk to me, I kind of was following up on our conversation from last time with Ellie Pavlik about what do you make of these large neural net models that seem to be doing magical things. And I had a wonderful conversation with James Tompkin, one of the faculty members in my department, who works in, I guess I call it computational photography. I don't think that's how he introduces himself anymore. But to me, computational photography is such a cool idea because it's like computer graphics is, bits in, pictures out, and computer vision is like pictures in, bits out. But if you've got pictures in, pictures out, that's computational photography. And James has done a lot of really interesting work in that space. And these days, neural net models have kind of eaten all three of those fields. And so I figured James would have a really interesting perspective on this. And he did. And guess what, Dave?
I don't know. What?
He agreed to come talk to us. So let me
right.
introduce you. This is James Tompkins. Thanks a lot for being here.
Hi, everybody. How you doing? Yeah, I think I officially call myself a visual computing researcher.
Yeah, that's cool, because that feels like it really does get the whole picture part of it, right? That's because
right.
That is the commonality between all three of those.
That's right. And then I get to pretend that I live in all different kinds of communities as long as I'm dealing with visual things, visual images, right?
Like so what are some other things how else do visual images come up in computing?
Oh, well, the classic approach that you described of graphics as being synthesis and vision as being analysis, and this sometimes we like to say that there's like a cycle between these two, but really it's for a long time been a dream to be able to exploit this kind of a cycle. Yeah, so anywhere that images crop up. My background is in computer graphics, really. But as you said, as soon as you're dealing with cameras, then your goal is to solve the inverse problem of recovering some useful representation of the scene such that you can then edit it. For computational photography, that means things like doing defocus, blur for the background, things like that. That's the classic example that people talk about, which now is built around machine learning models rather than a more like physically based estimate of the depth of the scene.
So I guess I've it makes total sense that that's what's happened, but I guess I had missed it. It seemed that computer vision specifically had done a tremendous amount of very detailed work about understanding optics and field light fields and all of that stuff.
Yeah.
And are you saying like we just toss all that crap and do pixels to pixels with TensorFlow and call it a day?
That's a great point. So maybe 5 years ago, there was some kind of optimism that was maybe possible, right? That the people trying to solve these kinds of problems said, well, if I can do that with deep learning, then maybe I can do this crazy stuff where I don't need any kind of physics anymore, and I'm just going to learn physics. And that's really hard. And it turns out that we're not very good at that. And so the graphics people are still relevant. I think that's the thing that we're most pleased about. that we're still relevant, that we can imbue all of this knowledge of physics and sampling and rendering that we've learned over the past 50, 60 years and actually make contributions extending into AI as well.
And so that can't just be saying like how many hidden layers you should have or something like that. Right. It's got to be somehow more structural. Can you give an example of how that kind of comes into it?
Yeah, I can. So projection is the classic one, right? We have a three-dimensional world that we sense with two-dimensional cameras. And as soon as you want to do any kind of inference, trying to solve something back in the 3D domain, I need some kind of physical model of a camera. And this is a hard problem. It's opposed. It always has been. Classically, computer vision has tackled this through multi-view geometry, like the process of using multiple cameras to try to image things. But it turns out that if you want to solve any problem, really, in a three-dimensional world, it's really, really useful to have physical models of cameras, not just physical models of cameras, but also ones that you can optimize through. So what you might call like a differentiable model of a camera. And then we get into all of this new work that's happening in graphics right now about how I do what's called differentiable rendering, which is complicated, but is powering a lot of the newfound amazing results in the computer vision, machine learning, and computer graphics communities.
Okay, wait. Can we go through that a little bit more slowly? Yeah. So rendering. So people have seen movies where where computers are somehow involved in the imagery, and the way that we should think about that is that somewhere in a computer someplace is like a 3D model of the things that are supposed to be there. And rendering is the process of saying, what would that thing look like if you placed a camera here? So it kind of works out the math of, you can see which surfaces, and here's how the surfaces would look, and here's how the atmospherics in the air would cause it to blur a little bit. And so you get this photography simulation, right?
Yeah, that's exactly right.
That's rendering?
Yeah. So classically, painters would be human painters would be the algorithm that turned the scene onto a canvas, right? They performed that process. But since the 60s, we've asked computers to do this for us. So we specify mathematically what the scene should look like, and then we specify mathematically where the camera should be, and then we ask an algorithm to paint the picture for us.
Okay, and so yeah, I kind of remember from art class in elementary school, they actually did have us take a ruler, and they said, like, here's the object and here's where the lines would converge. And there was perspective, I guess is the word that I remember from that time.
That's right.
And when I learned how to do that, then I could draw boxes really well. Like my boxes were so good. Like little brick walls. It was just, It was fantastic. Now, like human bodies and stuff never ended up being okay for me, but boxes, I kind of got the boxes down. So that's rendering. So when you talk about rendering being differentiable, what? So differentiable, we need differentiable when we're doing neural nets. The idea of differentiable is that we can we know enough about how the calculation is taking place in a learning algorithm, in an algorithm, in the thing that the learning algorithm is trying to learn. And what that lets us do is to say, if we were to change it a little bit, here's how its success would change. So I think I understand differentiability in that context, right? Because it gives us a guidance as to how to change the thing being learned, the program essentially, so that it does a better job of matching the examples.
That's right. It's the way of defining how we should tweak the scenario such that we get the right answer. And so when we think about drawing things or rendering things, oftentimes we're posing a problem where we have some kind of photograph that's been captured of the world. And I want to say, what was the true shape of that object?
I see.
So my objective...
So we're not differentiating the calculation. We're differentiating the elements in the scene. Right?
That's exactly right.
What are you seeing?
That's right. It's to say... So suppose I took a photo of a teapot, right?
Never done before.
And I said I'm going to initialize some geometry in my computer that's going to be a sphere, let's say. Okay. And I'm going to look at the photograph, the real photograph, and then I'm going to render the sphere, and I'm going to say, in what ways is the sphere not like the photograph of the teapot?
Or our rendering of the sphere look like
exactly,
the photograph of the teapot. Got it.
Right. And then I say, well, how should I change my input such that it looks more like the teapot?
And it can now deform the sphere. Now here's my handle and here's my spout.
Exactly. Now, of course, I'm going to run into trouble because the genus is wrong. The teapot is actually a donut, right? Because it has a handle. Right? So I have very complicated problems when I try to pose this kind of a question, because I don't necessarily know what the scene has in it ahead of time. Right? So in that particular case, I'm always going to get a little bit stuck. So it's a very complicated problem.
And so in that particular example, the fact that you actually needed to punch a hole in the sphere in order to make it more teapotable, is that an example of a lack of differentiability?
That's exactly right, yeah.
Right. And I mean, I see these papers going by over the last, I don't know, a decade or so about people making everything differentiable, including things like arbitrary sequential programming, which seems to me like the poster child of non-differentiable.
Right.
Everything is a hard step. Everything is 0 or 1, not continuous, not nothing. And then I read this thing, differentiable Ackermann's function or something. I don't know what. Like that. And I can only guess that just making something differentiable doesn't mean the derivatives are going to be well behaved, right? That's the trick, right? That we may or may not be able to actually use this technical differentiability, or we might get stuck on the planes and have no idea where we're going.
Yeah, that's very true. Yeah. The classic non-differentiable problem in graphics is visibility, or ordering. Like when you see something or don't see something because something has moved behind something else. That's a problem of differentiability. It's a discontinuous, yes. And so we've come up with all of these soft, fluffy formulations of our algorithms that try to get around this, but may not have guarantees.
Which is kind of like is it kind of, I was going to say it is, but let me say, is it? In physics engines, when they're doing simulations of hard body collisions, they get these incredible nonlinearities when things run into each other. So they have to kind of soften them up. They actually soften up hard objects just to avoid the numerical problem that would cause objects to go spang off to infinity. It sounds kind of the same as what you guys do to make your occlusions,
right, to be able to reason about those objects. Yeah.
I wonder if that has anything to it. I don't know. I mean, my thing is, I know nothing about computer vision except, what I can do with OpenCV, and I don't even understand that. But it feels to me like the research that comes out of it. I mean, what I love about computer visiony research, and maybe you can help unpack this for me, is there's so much stuff that seems to be so hard, but there's a sort of a trick as to how to approach it, which is to say, well, we really need to know where the camera is and what it's looking at, and either of those could be wrong, and we don't know either of them, but we're going to magically solve them simultaneously,
right.
like that. You know, and I see that being applied more and more and more and more. It's like, you know, assume this. And how does that work? Or when does that work? You know?
Well, it works when your initialization is sufficiently good. That's the
and something about the problem as well. I assume it must be smooth or attracting-y or something.
Right.
Like that.
One of the things we found, many disciplines have found, right, but when approaching the kinds of problems that we're talking about, over-parameterized neural networks, so very, very large neural networks, are very good at solving problems that we didn't think would be otherwise solvable. And it turns out that they produce actually quite nice results, even when we would normally expect them to produce horribly overfit results. And so this is one way that we've found in the past few years that we're able to make progress on some of these very difficult problems.
Don't worry, just throw more weights at
more
it.
layers.
And, more layers, more weights.
Yeah.
And it will throw them away. It will waste them for you.
So, well, there's some truth to that, right? That this thing is naturally compressive and that you get a great benefit from that. I'll say that the big revolution in sort of an area that I work on, scene reconstruction, has been these things called neural radiance fields recently. And
neural radiance fields.
Yeah.
Okay.
Let's just
Those
say
are cool words.
They are. I'll explain it very simply.
Yeah.
It's a nice order.
Beyond just having a big neural network, right? The idea is that if I add some of this physics back in, I can then start to reap all of the benefits of making the 3D understanding into the neural network model. So neural radiance fields say there is density in the world and there is light in the world, right? And I start my problem by saying,
sounds a little religious somehow.
It's true.
You are my density.
And also, we'll start with one assumption. Let there be light.
Yeah. And I can put density and light in various different places, right? But wherever I put it, it must conform to a three-dimensional reality, such that when I look at an object from one view in a camera, and then I look at an object from another view in a camera, wherever I put the light and wherever I put the density should be consistent with these multiple views, right? And so the neural network does all the heavy lifting of saying where should the density and light be, but the product must conform to this three-dimensional physical reality. And that works a treat. It actually is stunningly good and has led to just a huge explosion of work over the past 2 or 3 years and rapid progress.
Okay. So for people,
let me understand that a little better. So you're saying you're going to start with essentially pixels or pictures from a video frames or something like that.
That's right.
And you're going to have a neural net that is going to postulate densities, blobs in 3 space, and light sources also in 3 space that it thinks would account for this particular image we're seeing.
That's right. Actually, it's even simpler than that. Light just sort of comes out of everywhere, and where it comes out of or not is the reproduction of the scene. Yeah.
Oh, and that's a radiance field, right?
That's a radiance
radiating.
field. Exactly.
And it's a field in the sense that it's a function over space, right?
Over 3 space. That's right.
Okay.
And wait, and it's uniform light that's coming from everywhere, or it's being configured?
It varies. Yeah.
You're learning that it's bright here and dim there.
The neural network says how bright it should be at each point.
I see. So what we would have considered a light source is just a peak in the radiance field in 3 space at that spot.
That's right.
Like that. And that's enough. You show it a terabyte of cats, and
actually no. This isn't a deep learning method. You don't need to show it multiple thousand images of cats. You just need to show it the few examples that you do have. So say you take 30 views of an object spherically around, and that's sufficient to produce the final form of the object.
Wow.
So it's very powerful.
And in particular, it's not about using gradient descent to train on large data. You're saying it's using gradient descent as an optimizer to figure out what makes sense out of these images that we're taking of this one shared object.
That's exactly right, Michael. Yeah.
And okay, because
but then does it fit with the? Okay, yeah, go ahead, Dave.
Well, no, I was just going to say, I tried to do one of these 3D reconstruction things where you take a bunch of images of your thing and then you put them in and it finds the correspondences and blah, blah, blah. And what a train wreck that was. I never managed to get anything. I was trying to get my face, because I was trying to build a mask for the pandemic, out of 3D printed crap.
Amazing.
Yeah, and it was hopeless. It was a big disappointment. And so what you're telling me is I should have used nerfs, the problem was I didn't know how to use any of this. I was just downloading software from the internet, and I couldn't get any of it to work. But this is the kind of thing that would help with, right? I mean, if the software was shined up, and
that's right. Yeah.
Wow.
And there's this. The interesting thing to think about is how the problem is posed. So we say that there's this just random stuff and light at the beginning, right? And it seems incredibly difficult that you're ever going to get to the right solution where you just start with this random ephemeral stuff, right? But the neural network and the gradient descent is able to find a very plausible solution to the field that does reproduce photorealistic images back.
Super cool. So which says that the 3D images, the 3D worlds that we're asking this thing to reconstruct have a certain simplicity in blob space, in density space, or whatever it is. And if it was like a 3D version of static, like a solid version of the HBO logo, then it might not work so well like that. But that nobody cares about that.
Right. But somehow the assumptions or the regularities in the world and the assumptions in the model line up.
Well, it's explicit. So we say that the way that we produce the final image must be through the rays that get traced through this volume of stuff, right? And so it's almost by construction. You can think of it as a neural-based way of solving the very old correspondence problems that Dave was talking about that were solved by his old software. But we get this great robustness for free from the fact that we're using these big capacity MLPs, neural networks that are trainable to great results, like surprisingly good results through gradient descent.
All right. So now make sure that I'm going to say something that's probably wrong, but help me get me back on track. So, all right. So all this computer graphic stuff depends on having these kind of 3D models of space and what's going on in space. And now I've been, reading on Twitter that there's this thing called DALL-E 2, and DALL-E 2, you can just like DM it a description, and then it produces like arbitrary artwork or photographs or 3D like graphics models, like anything you could ever visualize. It just draws it for you. And so we don't need computer graphics anymore. So it's been nice having you on the show. Thank you very much.
Bye, everyone.
But we're no longer necessary.
Yeah, I said we were relevant, but I'll get my coat. So DALL-E 2 are amazing. Really, really amazing. They do work by training on very, very large data sets. And
just to ground us, like, do you know what's in the data sets? It's images and like captions, or is it images and like all the text like of Wikipedia, or
it's images and captions? Yeah.
It's just, and so all it knows about language is the language that's used in captions.
That's right.
That's so interesting. Okay.
And so you can ask it to produce you an image of teddy bears on the moon conducting scientific research in a 1980s style. And it will, which is one of the examples from OpenAI, and it will produce you a plausible looking image of those teddy bears on the moon, which is really stunning. The first time you see it. So then the question that Michael is alluding to is, well, are we done, right? And the graphics people clinging to their relevance to say no, but we're not quite done. And the question comes down to control. And it also comes down to the task you want to solve too. So for many applications, DALL-E 2 may be enough, where you say, oh, I want a picture of a panda riding a motorcycle with a red scarf, and it comes up with some image of a panda, right? And that might be fine. That might be all that you need. But then if you say, well, I want the scarf to be blowing in a slightly different way, right? Or I want the panda to have a slightly different shaped head or something like that, right? Then it becomes very difficult to know how to specify, how to make that change. The only interface you have is through text. And it's basically impossible to specify those kinds of fine-grained edits, even if the model would have the capacity to produce an image that did have those variations, which it probably does. The interface to it is not able to expose that to the end user. So a lot of what graphics cares about as a discipline is how to elicit creativity from human beings through all different kinds of interactive systems for declaring scenes for movies that Michael was talking about earlier, for example. So this question of control is very important. We were talking with Stephen Buck, another of our colleagues, whose partner is a graphic designer. And he was saying that
a human graphic designer.
That's right, a human graphic designer. People have very exact specifications on what they might want to do, and that's intentional. It's intentional, and that intent is difficult to specify exactly with the current models that we have for learning-based image generation, as impressive as they are. So graphics and the history of knowledge that we've developed and the tools that we've built will start to be integrated into a lot of the large learning-based models sometimes through physically based models like we talked about, through 3D reasoning, things like that. Other times through more formal specifications, through other types of programs, perhaps. So all kinds of different things that will build towards a more flexible image generation system.
Okay, so to one way that we're not done, and the graphics is not irrelevant, is that one of the reasons people want to make images is that they have particular images that they want, and describing them in words and then just hoping, crossing fingers and hoping that the image that comes out is exactly what they want isn't really a solution, right? Because it'll be something, and it might even be cool, but it's very highly unlikely to be the thing you actually wanted as a, I don't know, client or as a storyteller, even, right? If you're making
as a storyteller,
a movie. Yeah, right. So I kind of encountered this a little bit because I wrote a book and I wanted an illustration of a Mars rover looking at a map, being kind of confused, like holding the map upside down, like not knowing where to go on Mars. And so through channels, I managed to get this to DALL-E 2, and they sent me back an image, and the image is it's great. But it's not what I pictured. And if it were a person drawing it, I'd be like, well, could you have it holding the map? Like, I don't want the map on the ground. I want it to hold the map, and it should be visibly inverted because that shows that the rover is confused. Instead, what it did, I said confused in the description, and it did have the rover's head was a little bit askew. So it did convey a little bit of that. Like, it wasn't terrible. And as a one-shot thing, it was fine. But I really did want to go back and say, no, I would like it to be on Mars, not just a red floor was what it looks like. It's like a red linoleum floor. I wanted it to be like sandy, dusty, dirty. Okay, so I think I get that.
Another area where this is important is when we think about what we're going to use these systems for. So when you think about large learning models, you think about the spaces, like the embedding spaces. I don't know if we've used this term in the podcast before, but like the hidden codes that they learn to represent concepts For many, many tasks, we care very much what the structure of those relationships are, right? And it's important because it gives us it might give us certain guarantees about what the model will do. It lets us perhaps explain results that the model does produce. And many of the problems that we're going to pose AI models in the future will be based around understanding of the physical world to produce plausible results. Right? And so this is another area where it's important that this kind of 3D reasoning, this kind of control, or this kind of specification has a way to influence these models, or be a constraint perhaps on these models to give us more reliable downstream tasks or more explainable answers to why the model came up with a particular answer.
I mean, I keep thinking that all of the stuff that I'm seeing now, GPT-3, DALL-E 2, and so forth, are all really leaning on this kind of one-shot approach, that they're kind of stateless, and that's seems to me sort of their Achilles heel at the moment. And now what I'm wondering is, it seems like it wouldn't be that hard to take like the previous image and provide that along with the caption as a learning task, except that you haven't got terabytes of previous images to go with captions to get your improvement. Or the same thing with GPT-3, where you could take some previous text plus a new prompt, a more conversational thing. And I don't know. I mean, I kind of have to believe that Facebook and Google and all these people are doing that stuff already. They're trying to do stateful learning, but it seems much harder to come up with the terabytes of data. Do you have any insight to that? I mean, okay, it's an unfair question. Well, but we could take it in a different direction. I saw on your page that you were also interested in HCI, in human computer interaction stuff, right? And that's kind of, this is sort of a task. What we really want is we want an interactive program where I can say, I want a ball, no, like a beach ball, and no, not blue, no, and with hair, no, I want a dozen of them, and I want them in a grid. And the picture just keeps changing and changing and changing and changing, and then I say, okay, figure one. And then I go on about my business, like that. But the emphasis there is on the interactive.
That's right.
Right. And do you think there's steps to be taken?
So on the language side, my understanding is that we're getting there slowly. That actually we've made significant progress.
Oh yeah.
Maybe Michael disagrees, but.
I mean, I know that the efforts that some of these folks have made to make programming interactive are proceeding. I don't know if my guess is that they're actually not adequate. They haven't really been tested by HCI people, but the codex system and the Copilot system that OpenAI put together, where you use language to describe a program, and then the program just like poof, it just appears, and then.
But once again, it's one shot, right?
No. So in the demo video that they provide, they do this. So like they describe it, and then it produces code. And they're like, actually, like I want there to be an error message, and it produces an error message in the code. And it's like, no. I want the error message to be a little bit more friendly. Or even I want it to be a little more friendly. Like you can even use pronouns, and it would, in the context of this interaction, it can actually resolve some of those pronouns sensibly. So
the code is getting fed back in. The code is getting fed back in somehow. So it is stateful in that sense, or something.
Yeah, but using the same trick that all the language models use, which is like, it's always doing completion, right? You give it context, and it's like, well, what comes next? And so what comes before the next is this changing conversation. And so it has that context right there in front of it.
Right.
But that being said, the experiments that I've done interacting with it have been not as good as what they showed in the video, right? So it's not really been run through its paces by real HCI people. I think it's machine learning people who have been like, wait a second, this is amazing. Let's show how cool this is, as opposed to, we're going to evaluate what's is this like when you're interacting with actual people and trying to give them the results that they actually want.
So I can say from the graphics community, for a long time, people have been trying to use assistive like machine learning techniques to provide tools that artists, for instance, can use in the process of their creation. And many times they are good, but not good enough, because either they will get you 90% of the way there, but 10% will be just wrong, or they will change the previous answer when you make some little update somewhere, right? Like I just wanted to make a minor change over here, but then something else changes in the other part of the image that I really didn't want to happen. Right? And so classically, the problem has been, well, am I just going to fight this system to give me what I want, which will just take me longer than if I just do it all myself anyway. So you really need to get past quite a high threshold of, I don't want to call it like artist pain tolerance for correcting all of the mistakes that the machine learning model might make, and actually be a useful tool.
So, but in your work, you do some interactive stuff in your own research, right? So why don't you tell us like one of your projects? How do you attack the problem that Dave was raising? It's squirming. You're squirming in your chair. It's hard. You do this, right? Okay, well, sorry. It's hard.
The problem, no. So the problem is about intent, right? I'm trying to discover the intent of the human being when the human has a really clear idea, well, let's say that they do, of what they want in their head, right? But the machine has very, very little signal that you're giving it on what it is you actually want. And most instances where machines try to guess the intent of a human being fail horribly and end up being very annoying to use, right? Like Clippy is like the classic historical example of this, right? And oftentimes people just turn those things off because unless they're really perfect, they just end up being annoying. So as far as I know, it's still a challenge to build these kinds of systems. Yeah.
I mean, so to even talk about intent, there's kind of it seems to me kind of a language of intent, kind of conceptual structures of intent that are not evident in pixels in any way you slice it. And sure, the big magic of deep learning is that it infers hidden representations that do the job. But it doesn't let us name them. It doesn't let us name the internal representations. Now, I mean, I would suppose more complex systems could do that, saying, I want you to draw a picture of bears on the moon. Well, but I mean, I guess those are supposed to somehow be naming hidden structures like that. So, I mean, how do you even begin, I guess, with intent? What is trying to recognize intent even mean?
Right. Another question is that oftentimes language is ambiguous about what we really mean, which is incredibly confusing for any kind of database learning method. But human beings have somehow a more principled or abstract understanding of the concept behind the language. And that can also be a confounding factor. Yeah.
You mean because we're not starting with the language, we're starting with the state of our brain.
Right. The sensory experience and
pasting together some words, it can't mean bank as in riverbank. It's got to be bank as in money, whatever. And we don't even think of the other things, but our pitiful little computers still. Like that. But I thought that deep learning was supposed to have fixed all that. I thought that deep learning was supposed to now take context into effect and always come up with bank the money, bank the river, bank the shot. And I don't know, maybe so, maybe not. I mean, it seems to be doing better than it used to. I mean, Michael and I were both back at Bellcore when Tom Landauer's group was doing latent semantic analysis and all that. And, we were so thrilled to be able to disambiguate anything with anything because the bags of words are different, like that. And all right. Well, I'm supposed to not keep starting new topics.
Why not?
well, I want to know about your creative exhibition at the Museum of the Moving Image in New York City.
Oh, okay, sure.
I like that. I mean, I've always wanted to go to the Museum of the Moving Image. I never have. But I think your link that you got is dead. So I went looking, trying to find out what it was about. And I couldn't. So now I get to ask you, what was that about?
Sure. So this is a while ago now, but I worked with filmmaker and artist Jeff Dizom, who's Luxembourgian, and he had this brave idea to take Hitchcock's film Rear Window, which is classic in that and renowned in the way that it's shot. It's shot mostly through the lens of a camera of a character who's peering out of a window, looking around a scene, right, trying to uncover
Jimmy Stewart in
a
wheelchair.
Right. His
leg's broken. Yeah.
His leg's broken. Yeah.
That's right. He's trying to uncover the murderer, right?
Right.
And so Jeff and I worked on a piece. Jeff stitched together all of the shots independently into a panoramic view of about a 20-minute reel, and then he added some nice like weather effects and things like that in post. And then we built this out into an interactive exhibit where you could pretend to be Jimmy Stewart, like looking through the lens and looking around the environment, that kind of thing. And so you could for a time you could go to the Museum of the Moving Image and go and play with this thing.
Very cool.
Yeah.
So I mean, could you solve the murder too? I mean, if you looked in the right direction at the right time?
Yeah. That's exactly right. Yeah. The modern twist was that your camera shutter didn't, send the photons to the chemical film back. It sent it up to Twitter, where it posted a little graphic of what you were looking at the time.
Oh, super cool. And how did you get connected to that? How did that come to happen?
We had a research project actually that tried to look at how we can navigate large collections of videos within panoramic imagery. So Street View, for instance, at the time, this was about 10 years ago, Street View data was around, a new thing. And then there were street level videos of people captured on their cell phones, right? And we wanted to be able to embed the little videos within the panoramic imagery. And we said, well, if it's not just one video, what if it's 20 videos? Like, could you get a sense of a place and the activities that were happening if you could perform this this kind of a reconstruction task? And then we built out an interface for it, and I think Jeff saw it, and he was like, oh, I've got a thing that looks suspiciously similar to this, where I've taken all these videos from Rear Window and stitched them all together, and the rest is history.
And so the views from the Rear Window, I mean, it was looking out on another building, right?
Yeah, over a courtyard. That's right.
Okay. So there is some three-dimensionality to it. It's not just sort of like panning back and forth across a two-dimensional thing.
It's a good question. If you rotate a camera exactly around its optical center, where all of the rays converge, then it truly is rotation. And only if you move the camera away from that optical center does it become three-dimensional.
Because you'll never see anything if you're actually going around whatever it is, the focal plane, whatever you were talking about.
The optical center.
Optical center, yeah. You'll never see anything that you wouldn't have seen from with the camera in another. Well, I mean, you'll see stuff on the edges, but you'll never see behind anything.
That's right.
You never go laterally.
That's right. It's called parallax.
You
never induce parallax.
Different movie.
Is that a movie?
Parallax View. I don't know. It was a thriller.
It should be.
Anyway,
we should do that one next.
Well, so. That's great, and I'm supposed to shut up. But instead, I'm just going to ask you, what do you think is coming next? I mean, whether you want to take that in terms of what you're interested in, or where you think the field is going. What's next?
I'll punt on where the field is going. So the fact that we're getting good at doing 3D is changing things rapidly. So we used to only really concern ourselves with 2D database learning, but now we can start to approach 3D database learning. It's much more computationally expensive, but really the big bottleneck was there wasn't any data. And now that we have reliable, or we're soon to have reasonably reliable reconstruction methods, it will be possible for people to go and collect all manner of three-dimensional objects as training data, especially because of the smartphones in our pockets that are now very, very capable sensing platforms or systems. So people are starting to build out large-scale 3D data sets, particularly of objects. It's very useful for things like robot manipulation, to be able to pick things up. And so this will be a new direction where we try to build efficient models that can handle all of this 3D data and still learn priors over 3D scene structures rather than just over 2D scene structures.
Cool. I would imagine that like the self-driving cars and stuff would be coming up with tremendous amounts of stuff that has inferred 3D. They have multiple cameras, so they can do the parallax and all that.
Yeah, well, this is one of the tensions, right? Because my understanding was that Tesla have a different opinion for how it should be done than everybody else, right? They don't go and sense the 3D ahead of time using something
directly,
like LiDAR. Right. They say, well, human beings can drive and we don't have LiDAR sensors. So our cars should be able to do it too. So even though I say that the future, we're going to be able to do all this 3D learning, maybe somebody will say, well, do we have to? Do we really need to? Because human beings, maybe we don't really work that way. And we seem to do okay living in a three-dimensional world.
Yeah, though we do grab things. Like we do get these other. Oh,
yeah, sure.
Like that matters, right? If we were just stuck in the window, right, just watching and never really be able to touch anything, it's hard to know how deeply we would understand objects.
I mean, certainly for me, the biggest elephant in the room for machine learning is that there still is this idea of learning and then being done. That training and then not learning, whereas humans are learning all the time, and that is important to their behavior. So, these adversarial images where you can take a machine learned thing and you can show it a static and it says it's a bagel or whatever it is, like that. And my bet is that if you could paralyze our eyeballs and hill climb against our brain, we could come up with adversarial images for us too. But what would happen? Right? Well, I mean, there's certainly optical illusions, but I mean more like those are persistent. No matter how many times we look at it, it's still a pain in the butt. But this is something that you'd say, you say, wow, that's a dog, and then you'd blink and you'd say, no, it's a car.
Whoa.
Like that, and because they had optimized against that, and because we can keep moving, because we're always learning, then that just becomes part of it. And I wonder how this whole model of deep learning, where there are terabytes of data on Gonzaga unbelievable machines, gets delivered down into a phone that can't do that, is going to kind of top out because of that. I mean, I don't know what to do about it except to say maybe that's good, But it's frustrating. It's frustrating because to me, I want to learn more about the interactivity between learning and performance, like that. It's sort of a more closed loop kind of business like that. Well, James, hey, thank you so much for joining us.
This welcome.
Is all incredibly fascinating stuff, and I guess we don't really know. Well, I guess so. Michael's question about whether DALL-E is it? We've kind of answered that. It's super cool, but it's not it.
Or it's at least it's not it for everything.
Right. And what's coming is the computer understanding three-dimensional space, not just flat pictures. That's right. So there's going to be no place to hide because it's going to know you are behind the trash basket, like that, and we're all in trouble.
Forgive me.
Yikes.
James, thank you very much.
A pleasure to be here.
This was Computing Up. Thanks for listening.